You're fine. Okay. So let's talk about some hidden features within this problem where you have this 2016 number 4. So you have a Ka of 1.12 times 10 to the negative 10. Okay? Judging from your vast experience as a chemist. Is that a relatively small Ka value or a relatively large Ka value? It's relatively small. Okay, a lot of Kas are 10 to the negative 4, 10 to the negative 5. Okay? So what this means is that's a pretty weak acid. So what does you know then about the conjugate base? Very strong. So remember, there's an inverse relationship. So if you have a really, really weak acid, remember what makes it a weak acid is the fact that it exists over here in the molecular form. So A should not give you any trouble at all. If you cannot do part A without any hesitation, I have failed you. Okay? Literally. Now, but remember, if you're taking this test, you are trying to convey to the grader who doesn't know who you are, that you understand how chemistry is done. Okay? You don't necessarily need to write out the entire equation, but you need to throw them a bone and go, hey, just don't randomly write down the pH and go, hey, that's cool. Okay? At least, okay, set up that rice chart. Now, you don't have to go to the other extreme either. You don't have to say, you don't have to write a note that, hi, you don't know me, I really like you. I'm going to set up a rice chart. I'm going to assume that the subtraction from X isn't significant. And you don't have to go to that extreme either. Just show them this. Everybody understands a rice chart. So you do this and you get done, and they've never had to do this, you've never had to worry about the subtraction of X being anything to worry about. So you do this and you get the Ka equaling X squared over 0.75, and to do all of this, you get a pH of 5.04. Okay? So that's what you should end up with as your pH. Now, here's the tricky part. And it's rare that I read a question and I think, man, that's a good question. I wish I would have thought of that. B, I had that moment on question B. So here's the whole point to this. Certain reaction involving this thing with the hydroxide ion. Phenol must primarily be in a deprotonated form, which is a fancy way of saying that we're going to take off a proton. Okay? Basically, it's going to exist in that ionic form. So the reaction must be conducted in a buffered solution. On the number scale below, circle each of the pH will 50% of the phenol molecules in the deprotonated form. Okay, so the only way you can really do this is start with that Henderson-Hasselbalch equation. Okay? So you know what the Ka value is. So you can find the pKa value, which is like 9.95. Okay? Now, so right away, would phenol be a good weak acid to use if you were to make a buffered solution of, say, around 6? Why not? Yeah, way too far off. Remember, the pKa value gets you in the ballpark. Okay? So you want to choose, if you're going to do buffered solutions, you always want to pick a pKa that's close to where you want to end up. You use that anion and HA values to find the seat within the stadium. So the pKa tells you what stadium that you're going to. This tells you, hey, this is where you want to be. Now, so think about this. As this reaction proceeds, you don't have to draw this chart, but it's handy if you understand this chart. So you're going to start off with some amount of acid and some amount of anion. Now, as the reaction proceeds, you're not going to lose very much of that HA acid. You're going to lose a tiny bit, but it's pretty much going to level off. You're only going to use a tiny bit. Your anion concentration is only going to go up a little bit, because that's what happens when you have a weak acid. Now, but think this through mathematically. I don't care what the numbers are, okay? But I want you to think about this. In what situation would the pH equal the pKa? When those two values are equal, right? When you have an equal concentration of your anion and your acid, right? That's, if you had a 50-50 split, that's when your pKa would be 9.95, which would be your pH. Now, here's the whole key to this question. It says, circle each for which more than 50% of the phenol are the deprotonated form. So if you look at this mathematically, you have 9.95 plus the log of the anion concentration over the concentration of the acid. Okay? So this is more of a, hey, almost to a certain extent, you understand chemistry and you understand logarithm. So it says that you more than 50% have to exist in this form. Okay? So let's say that this was 0.51 and that was 0.49. I don't care what the numbers are. You just have to have a little bit more anion than you have the acid. Okay? So your anion concentration just has to be bigger than the concentration of your acid. So if this happens, when you take the log of a number bigger than 1 or less than 1, what do you get?
Bigger than 1 is positive.
Yeah, the log is going to be a positive value. So if you're starting there at 9.95, and the anion concentration has to be a little bit bigger than the concentration of the acid does for this reaction to take place, and then you're going to add that, or you're already at 9.95, 10 or more. There you go. So that's going to be 10, 11, 12, 13, and 14. So that's what I said. This is wonky mainly because of the fact that most of the time it's just like, oh, hey, we're going to neutralize this, we're going to react it with hydroxide. This one was, hey, basically, do you understand two things? Do you understand the Henderson-Hasselbalch equation? And do you understand the relationship with logs and that value? So yeah, so it's going to be 10 through 14. Okay. Now, look at that 2009 question. So there's some things I want to explain before you really get into this particular question. So you've got CH4 plus 2CO2 yields CH2CO2 plus 2HCO. Okay? So this is methane, CH4. You're going to react it with chlorine gas. So we'll talk a lot more about carbon structures later. But the short version of carbon is the carbon has 4 valence electrons. It wants 8. So this is relevant to what we talked about today in class. It has 4 goats. So carbon has like the split personality. It's bipolar. Because of the fact that it doesn't know whether it wants to gain 4 electrons or lose 4 electrons. Because it's like right in the middle. It's like, man, I got 4 goats. Do I lose 4 goats? Do I gain 4 goats? I don't know. So what carbon typically does is that it shares its electrons. So if you were to look at this structure, you got a carbon surrounded by 4 hydrogens. Now, you're going to introduce chlorine gas, okay, which is diatomic. So you're going to basically what's going to happen is that you're going to take 2 of these chlorines and you're going to swap them out for 2 of the hydrogens. So you're going to get a carbon, and then you're going to have 2 hydrogens, 2 chlorines, and you're going to make HCl. You're going to make hydrochloric acid. You're going to make the gaseous form of this stuff because it's got to be run at really high temperatures. So here's the story. This is basically like a replacement reaction. You have chlorine gas, the elemental form of that. This is going to come in here. It's going to swap things up. And you're going to make HCl. Boom, there you go. Now, this is what we briefly talked about today. When you break bonds in a chemical reaction, that requires the input of energy. When you release energy is when you form bonds. Okay? So in a chemistry environment, because biology, I say that because biology handles this differently. But in a chemistry environment, when you break bonds, that requires requires the input of energy. When you release energy, that's from forming bonds. So, right away, when you look at 3A, you have a 25-gram sample of methane gas that's placed in a reaction vessel containing 2.58 moles of chlorine gas. Even if they didn't tell you to, why would you know that 3A is a limiting reactant problem? Well, more importantly, you're given information about both reactants. Okay? So anytime you're given quantifiable data about both reactants, you go until the reaction stops. It's like you're making cheese sandwiches. I'm telling you the equivalent of this is I'm giving you 10 slices of bread and 6 slices of cheese. How many sandwiches can you make? Oh, cool. I can only make 5 because I got to have 2 slices of bread and I have 10 slices of bread, but there's 2 per sandwich. So based upon my bread, I can only make 5 sandwiches, but I got 6 slices of cheese, so I'm going to have 1 slice of cheese left over. That's the equivalent idea. Now, if I just said, hey, I've got 6 slices of cheese, how many sandwiches can you make? What would your answer be? If you're going to have 1 slice of cheese for 2 slices of bread, and I give you 6, and I tell you, the only information I'm telling you is that you have 6 slices of cheese. So what are you assuming? You're assuming that you have an unlimited amount of bread. The bread, you're not going to run out of bread. The reaction is going to stop when you run out of cheese. So with this situation, when you're given both, okay, you have to work it as a limiting reactant problem. Now, this is where you look at the big picture, and I'll show you why you want to look at the big picture when you're actually taking the test. And here's why. This is the classic example. So it says, identify the limiting reactant with methane and chlorine gas are combined. Now, because you have 2 possible products, what you want to do is convert the CH4 into like the CH2CO2 or convert the CH4 into HCl. And you have to convert them both into the same product. Here's where you want to be efficient in this problem. Because it doesn't make any difference which product that you choose to roll them into, the CH2Cl2 or the HCl. But if you look on part 2 on A, it says calculate the total number of moles of CH2 in the container after the limiting reactant has been totally consumed. So this is why you would be foolish to convert it into HCl. You could, but then you'd have to just rework part 2 because then it says, man, they wanted the CH2Cl2. Okay? If they don't tell you, you can pick whichever product that you want. But this is the classic example where you need to look at this whole problem and go, okay, hey, I see where this is going to go. They want me to end up in CH2Cl2. That's how you want to roll this problem. So, now, when you get to this next part, okay, and then I'm going to turn you loose. So this initiating list reaction involves breaking the chlorine-chlorine bond, which has a bond energy of 242 kilojoules per mole. So let me explain what this number means. You have 442 kilojoules per mole. So if you have 1 mole of chlorine gas, which would be, this is going to be important, you'd have 6.02 times 10 to the 23rd chlorine molecules. If you want to break the bonds of every one of those, you're going to pull them apart. That's why that's listed as 242 kilojoules per mole. So you would have to dump in that amount of energy to break all of the bonds that hold the chlorine together. Now, this is why you know you have to break the bonds, because it's existing initially as chlorine. These 2 are bound together. But what you end up with is a structure where you have the hydrogens and the 2 chlorines around it. I can't bond the chlorine to the carbon if the 2 chlorines are stuck together. So I've got to dump energy in to break the bonds that hold the chlorine together, and then I also have to break the bonds that hold 2 of the hydrogens to the carbon. So then I can form a new bond. So when you get to B, okay, keep in mind that that's 242 kilojoules per mole of chlorine molecules. All they want to know is how much energy would it take to break just one bond. So is your answer to B going to be a pretty big number or a pretty small number? Pretty small number. Okay, because that's how much energy it takes to break a mole of those bonds. Now, when you get to C, this is tricky. Because on C, they threw in a little quantum mechanics, okay, relevant to the lab that you all did with the crystal violet. So calculate the longest wavelength of light in meters that can slide the energy per photon necessary to break the CL-CL bond. So remember, energy equals either h times frequency, which is h nu if you're old school. But the problem is they ask you for wavelength. But remember, the speed of light is wavelength times frequency. So if you solve this for frequency, you get c over lambda equals frequency. So you can also write this as hc over lambda. So this E is going to be your answer to B. H is Planck's constant. You're going to have your equation sheet. You can look this up. 6.626 times 10 to the negative 34th joule seconds. You know the speed of light, 3.00 times 10 to the 8th meters per second. Solve for lambda. Okay, I'm done. Work that.